The year was 1996, and the European Space Agency prepared to unveil its next giant leap in space exploration, the Ariane 5 rocket. The launch was more than a routine mission. It was a testament to Europe's aspirations to dominate the commercial space race. This rocket was designed to carry 4 advanced satellites, each critical to advancing scientific knowledge and communications technologies. The mood was electric. Engineers, scientists, and dignitaries gathered to witness the culmination of years of work.
3, 2, 1.
As the countdown reached 0, the rocket leapt into the sky, its engines blazing a trail of fire and hope. But beneath the surface, a hidden flaw in the rocket software was counting down to disaster. As the rocket launched, everything proceeded as normal. But as it had a slight veer to the left, everything went up in flames. But little did anyone know that this entire mission had been stifled by a single line of code. In less than a minute, over $500 million and years of scientific progress was reduced to rubble. The Ariane 5 wasn't just another rocket. It was the crown jewel of European aerospace engineering. Designed to replace the highly successful Ariane 4, it promised twice the payload capacity and cutting-edge systems that would ensure Europe's competitiveness in the growing commercial space sector. The rocket featured advanced guidance systems, larger engines, and improved structural integrity. It was a giant leap forward in technology, a rocket built for the future. But with greater complexity came greater risks. The mission wasn't just about delivering satellites. It was about sending a message, a declaration that Europe could stand with some of the best in aerospace engineering. But with greater ambition comes a greater risk. And sometimes the consequences far outweigh it. The Ariane 5 systems were built to handle immense challenges, but the very systems that were supposed to make it resilient became its Achilles heel. Hidden within the software was a line of code with a small bug that went unnoticed, but it was so critical that it would bring down an entire mission. As the countdown reached liftoff, the launch proceeded flawlessly. The engines roared to life, pushing the 777-ton rocket skyward. Cheers erupted in the control room as the Ariane 5 soared into the clouds. On the surface, everything was perfect. Let me stop it right there. So where did everything actually go wrong? So the main cause of the Ariane 5 disaster was hidden in the rocket's software, a tiny piece of legacy code taken from the Ariane 4 rocket. This code was designed to handle calculations for the rocket's Inertial Reference System, or IRS, which continuously measured the rocket's velocity and position to make sure that it stayed on course. And here's where the problem began. The code was written to convert a 64-bit floating point number, which is usually used to represent precise and large values, into a much smaller 16-bit integer. This was never an issue for Ariane 4, since the way that it was designed made sure that the velocity value stayed within the limits of what a 16-bit integer could handle. But Ariane 5 was faster, much faster. Its horizontal velocity exceeded the maximum value that a 16-bit integer could represent. Alright, so let's break this down even further. Computers store and process data in binary, sequences of ones and zeros. A bit is the smallest unit of information, and the more bits that you have, the larger the range of values that you can actually represent. A 64-bit floating point number is designed for high precision, and it can handle extremely large values because it reserves bits to represent both the number's magnitude, also known as its sign, and its fractional parts. On the other hand, a 16-bit integer can only store whole numbers within a very limited range, between -32,768 and positive 32,767. Alright, so taking everything into account, let's look at some actual code. So the rocket's code is written in Ada. And here I have a code snippet with two variables. Let's have a look at the first, which is the velocity. This line assigns the variable velocity to a float, and the value is 123.45. The second line below that declares a new type in between the range that a 16-bit integer can handle, aka a 16-bit integer. And the final line is the one that would have caused the error, which is a variable called new velocity, which specifies that the type of our variable is int16, and it performs a type conversion from the floating point to the new type that we created. And this new type, int16, can't handle the number as the velocity updates and the numbers get larger and larger. Now picture this. Imagine trying to pour a gallon of water into a shot glass. The excess water spills out. In this scenario, the excess water caused what is known as an overflow error. Yeah, I know, pretty fitting example. And in the case of the rocket, the horizontal velocity exceeded what a 16-bit integer could handle. And this caused the system to essentially scramble the data. Instead of gracefully handling the overflow, the software tried something new. The scrambled data fed into the primary IRS system caused it to crash. Worse yet, the backup system, which relied on the exact same code, did as you'd expect, the same thing. Without a functioning guiding system, the rocket's control system interpreted this failure as a catastrophic event. Since the rocket had no clue what to do next, it did as it was programmed. It activated the self-destruction sequence to prevent the rocket from crashing. And with that, a $500 million rocket was taken down with a type error. For the engineers and scientists involved, the loss was more than financial. It was deeply personal. The Ariane 5 represented years of effort, innovation, and teamwork. Watching it fail so abruptly was a moment of heartbreak. The investigation uncovered a startling fact. The legacy code that caused the error wasn't even necessary for Ariane 5's mission. It had been included because of a decision to reuse parts of Ariane 4's software to save time during development. While this practice is common in engineering, it requires rigorous testing to ensure compatibility. Despite the tragedy, the Ariane 5 program eventually rebounded. Engineers revised the software, introducing stricter error handling, better backups, and thorough review of legacy systems. The revised rocket went on to complete over 100 successful missions, becoming a cornerstone of Europe's space program and a symbol of engineering excellence. Each success following the failure carried a deeper meaning, proof that innovation is not just about avoiding mistakes, but about learning from them and improving continuously. The Ariane 5 wasn't just rebuilt, it was redefined. The program became a global standard for how to adapt, persevere, and succeed after a catastrophic setback. The Ariane 5 disaster didn't just change how rockets were built. It changed how engineers thought about complexity and risk. The lessons are now taught in classrooms and engineering labs worldwide. They emphasize the importance of simulating extreme conditions, questioning inherited practices, and ensuring that backup systems are genuinely independent. And on another note, perhaps the most significant takeaway was this: software, which is often overlooked compared to physical hardware, is just as critical to mission success. Errors as small as a missed boundary condition or an unchecked assumption can cascade into catastrophic outcomes. And when code is unchecked, bugs can happen. And when bugs happen, systems fail. The story of the Ariane 5 is a reminder of the stakes in engineering. A single line of code can cost millions or even lives. But it also shows the resilience of human ingenuity. Through failure, we learn, and through learning, we build better systems. And if you found this story interesting, make sure to like and subscribe, and let me know what you took away from the Ariane 5 disaster. I'll see you in the next one.